Welcome back to Calculus. Well, we are finally on for our last example here in trig substitution. And this one's really not that bad. You'll notice it's a definite integral, which is, we haven't seen one of those yet. That will be the main thing that's unique. Otherwise, pretty standard, maybe a little easier than the others. So this is going to be a trig substitution problem. We have a square root. We can't use u substitution because up top we have an x cubed. So let's jump right to it. So for x, we can build this thing, and we should be able to simplify it out. So this is a tangent one. So x is tangent theta, and the reason for that is that plus sign there. So remember, a plus kind of gives it away as being a tangent. And oops, I forgot my 3 tangent theta, because that 9 there makes our a 3. Get right into it and do dx is 3 secant squared theta d theta. Then we'll start building this right here. So I need to make that squared. I need to add 9 to it. And then that step, it always happens, right? You factor the 9 out. And the remaining portion is always the Pythagorean identity that can be condensed. And now you can take the square root of x squared plus 9, and that can be computed with no problem. So you get that to be 3 secant theta. You know what? I can go ahead and do that as well. If x is 3 tangent theta, then x cubed is 27 tangent cubed theta. I wonder if that arrow is going to be a problem. I think it is. I'm getting rid of it. Okay, let's get back to our problem and do our substitution. There we go. So and our bounds are going to need to change, but let's wait on that. So I'll just leave a little space so I don't forget. So my numerator is x cubed, or 27 tangent cubed theta. And then my dx is 3 secant squared theta. Let's put d theta on top or put it up front, however you want to do it. Or on the back, I suppose. And then the denominator we found is to be 3 secant theta. Wow, that's nice. The 3's cancel. The secant squared cancels up top with the secant below. And so we're left with 27, can come up front, tangent cubed theta secant theta d theta. Okay, let's talk bounds. So the bounds were 0 to 3. Well, what we've done in the past is you look at your kind of connection statement and you plug in your 0 and 3 right there, right? But 0 and 3 are x bounds, so I need to plug them in for x. So let's actually make a separate step for that. Call this aside 2. We're going to describe our upper limit, or upper bound, and our lower limit. Let's do that off the side here. So the upper one has a 3, the lower one has a 0. Those are the x. So it's going to be 3 equals 3 tangent theta, and 0 equals 3 tangent theta. So in the upper limit, we get 1 equals tangent theta, or theta is pi over 4. Yes, we're going to use radians always. The lower, you can divide by 3 and get tangent theta equals 0, so theta is 0. So my lower bound did not even change. It's still 0. My upper is now pi over 4. Okay. All right, well, this looks better than when we started, but not great. The integral of tangent cubed secant theta maybe looks familiar, even from the last section we did, trig power integrals. And notice the tangent secant combination there. We practiced many of those just recently. So you might remember the phrase that we always are looking for tangent to be odd and secant or secant to be even. So who met our request? Tangent. So what that means, and this to me is one of the more challenging things we do, is you pluck a tangent out, because you want it to be odd, it was, and put it at the end with your d theta. And so you're left with an even number of tangents, right? Which makes sense. You had an odd, you pluck out a single, now there's an even number left. That even number is going to be transitioned to secants. So everything will be secants, right? Because our secant term, in this case, is only just a single secant, but our secant term is already secants, right? So you pluck one of these out, the remaining, all the evens, become secant. So everything is going to be secant except that single tangent. You do, and what we know right away, I can go down and do this, I guess. We do know that our du is going to be secant tangent. And so our u is secant theta. So that single tangent is going to be part of the du. We need to also pluck a single secant. And in this problem, it turns out there is only a single secant, which makes it a little easier for us. So u is going to be secant. That's going to be my du. Before I do that, let's change that using Pythagorean identity. And we are going to need to change these bounds in a moment again. So the Pythagorean identity says this is what? Secant squared theta minus 1. And we have this. I'll just write it one more time. And now we're ready for our official substitution, which is just making this really long. So our u, oh, I already did that, didn't I? Right there. Get rid of all this. Good. Okay. So as we do that, we need to change our bounds. This is more of a traditional substitution, so I can just change them on the integral right there. And then this becomes u squared minus 1, and all that is du. That looks a lot better, right? Okay, what's secant of pi over 4? Well, it's the reciprocal of cosine pi over 4, which we know to be square root of 2 over 2. Reciprocal of that is square root of 2. You can check me if you like. Secant of 0 is the reciprocal of cosine of 0, which we know to be 1. Reciprocal of 1 is 1. Feel free to check me on that as well. And I guess I'll just leave this and we'll integrate next step. So it's going to be 1/3 u cubed minus u, integrating from 1 to the square root of 2. Let's see if we're looking good. Yes. You know, to make life a little easier on yourself, you might factor out the 1/3, because when you do it, it just becomes a 9. I'm just going to do that real quick. It's just going to make our work a little bit easier. So now we'll plug in, and this is square root of 2 cubed minus 3 square roots of 2 minus, better parentheses here, 1 cubed minus 3 times 1. So square root of 2 cubed, square root of 2 times square root of 2 times square root of 2. It's 2 square root of 2, right? Because 2 of them become 2, and the third one's just there. Minus that, and then this becomes 1 minus 3. So that's negative square root of 2 minus a negative 2. Or in other words, I think we got something here. 9 times 2 minus the square root of 2. That's a nice looking answer, is it not? And it confirms with what I have in my paper, even though I did it a little differently. And that's it. So changing bounds, you might want to look back over this portion to see how we did that with changing our upper and lower bounds. Otherwise, pretty standard the way we used our